Hello everybody, this is Dr. Christopher White, and in this presentation we're going to keep looking at igneous rocks. So this video is going to correspond to section 5.13 of your textbook. So in this video we're going to think about intrusions which are produced by smaller volumes of magma. So we're not thinking about the big intrusions like stocks or sheet-like plutons or batholiths. We're thinking about features which are produced by a lot less magma, and we're also going to think about how they are expressed on the surface of the Earth. So the first feature we're going to look at is a feature which we refer to as a dike. So dikes are sheet-like intrusions. They are often vertical to subvertical, so they are almost always nearly upright, and they cut across strata. So we can see that this dike here is cutting through these three layers of rock. Now, when a dike is typically expressed on the surface of the Earth, it's not uncommon for the dike to be made out of harder rock than the surrounding country rock. And so this means when erosion takes place, typically the rock either side of the dike will erode faster, leaving the dike exposed to form a linear ridge, which we can see on the surface of the Earth. So here's a lovely example right here. You can see the dike right there coming along the surface. So this dike once represented a sheet of magma that was being intruded through a sequence of rocks which have obviously now been eroded away, and because the dike is made of a more robust rock, it's eroded more slowly, and so we can see it's forming this ridge which is standing above the surrounding topography. Now, the next type of feature which can form due to magma being injected is a feature which we refer to as a sill. And we've already seen this term when we were discussing sheet-like plutons. So we can see in the case of a sill, we have magma being injected up along a conduit, which we can see here. The conduit in question would be a dike, so we've got magma being injected, and then the magma is hitting some kind of obstruction, or the magma has achieved the same density as the rock that it's trying to pass through. So the situation could be that this layer of rock here could maybe be impenetrable to the magma, so the magma can't get through it. And so what can the magma do? Well, it can spread laterally. The other possibility is that the magma is rising up and it meets this layer of rock right here, and this layer of rock has the same density of the magma, so the magma can't rise any further because the densities are equal. In that case, the magma once again will have to spread laterally because it can't keep going up. And this is typically going to result in a small intrusion. Typically it can be anywhere from a few centimeters to a few meters in thickness. So here we can see a lovely example of a sill. So we can see the sill is marked out by this rusty red coloured rock right here. So there's our sill. You can see it's got layers of sedimentary rock above it, layers of sedimentary rock below it, and you can see that the sill has gone and exploited the contact between some of these layers of sedimentary rock, and we can see that it's been injected laterally, so we can see it's orientated left to right. So the next type of feature that can form when a small amount of magma is injected into the crust is something which we refer to as a lacalif. So we can see that once again, here's our conduit which is feeding our lacalif, and this conduit is once again a dike, so it's a vertical conduit through which magma is passing. So we've got a dike underneath it, so the dike is representing essentially the plumbing which is bringing the magma up. And then, just like the sill, the magma is entering the sequence of rocks and it's getting trapped. It can't go any higher. That's either because, once again, this layer of rock is impermeable to the magma, so the magma can't get through it, or the density of the magma is equal to this layer of rock, so it can't rise any further. Now, instead of a sill, which is a sheet-like intrusion, what happens is we get the magma coming in and it causes the crust directly above the conduit to begin to dome upwards. And so the pushing of more magma into this intrusion right here pushes this area of the crust upwards, causing it to form this dome-like feature on the surface of the Earth. When we look at the margins of the intrusion, we can see they get narrower and narrower, and they eventually pinch out and disappear. So in 3 dimensions, this intrusion is going to have a shape something similar to a mushroom. So here we can see an example of a Lacalif. We can actually see this whole area of raised terrain here actually represents one Lacalif. So you can see here it is, it's coming up and it's coming down on the other side. So we're looking at this area here where it's coming up and it's coming down there. Now what's happened is the rock that was once above it has been eroded away because it's softer, and the Lacalif has been left behind, obviously because it's more robust rock. It will erode more slowly, so it's produced a topographic high. So the next type of small-scale intrusive feature is something which is referred to as a volcanic neck. So here we can see the general situation. So here's our conduit, which is bringing magma to the surface, and the magma is making it to the surface, it's being erupted, and it's forming a volcano. Well, typically what will happen is after an eruption, any magma that's left in the conduit of the volcano here will obviously solidify, and it will form solid rock. And over time you'll have multiple pulses of magma coming up, and each time those pulses, anything that's left over will get trapped in the neck here, and it will cool down and solidify. Now over time what will happen is the rock that forms the volcano will often be softer than the rock that forms the volcanic neck, and so the volcano will erode away relatively quickly. But the volcanic rock, the igneous rock in the middle here will be more robust, and it will erode away more slowly. And this will produce a feature which we refer to as a volcanic neck, and it helps us to see locations where volcanoes used to be situated, even if the volcano itself has been fully eroded away. And here we have an absolutely beautiful example of a volcanic neck. Now we can see that the volcanic neck itself is located in this area right here. So this is part of the conduit which is bringing magma to the surface and would be feeding a volcano which was located above it. Now there's still some bits of the volcano left. We can see some of it here, marked out by this kind of dark red-brown area, and we can see some of it here as well. So the volcano hasn't been fully eroded away. Given enough time, these rocks will be eroded away, and it will leave this area of igneous rock standing above the surface, and obviously we will see that as a volcanic neck. So not all volcanic necks form inside volcanoes. Some of them actually represent the conduit system underneath the volcano that was helping to bring the magma up to allow the volcano to erupt. So here we have a situation where we can see we have an actively erupting volcano, and we can see there's the central conduit which is bringing the magma up to feed it. We can also see though that we have a couple of smaller intrusions or smaller conduits off to the side, and these are paths along which magma is moving into the central conduit, and then that magma is being brought up to the surface and erupted. Now what we can see is that over time a large proportion of this brown layer has been eroded away. So we've lost the volcano, and we've also lost a reasonable amount of the central conduit as well. So what's left? Well, what we can see exposed here is the volcanic neck, which represents the central conduit. But we can also see that radiating from this volcanic neck we have several dikes. And these dikes represent the conduits which were helping to bring magma into this central channel here. So we can see a lovely example of this process here in the form of ship rock. So here's the volcanic neck itself, which is representing this area right here. Now you can also see though you have a line of elevated terrain there, there and there heading towards ship rock. So this actually represents one of these dikes right here. So we can see this represents a dike coming in to feed what would have been the main conduit right here, that would have obviously been feeding a volcano which was located above it. So the final type of feature which is associated with small intrusions is a feature which is referred to as columnar jointing. So if we look at columnar jointing from the side on, we can see we have lots and lots of columns, and these columns can sometimes be very, very large. They can sometimes be up to 100 meters in height. If we look at them from the top down, we can see that these columns actually consist of hexagons and pentagons. So if we look here, we can see we have one column that has 6 sides, 1, 2, 3, 4, 5, 6. Whereas here we have one column that has 5 sides, 1, 2, 3, 4, 5. So these columns are the result of cooling after the magma has solidified. So we can see here is our body of magma, and this is going to represent, in this case, a sill. And this sill is probably going to have a mafic composition. So the magma that formed in here, well, the magma was injected, sorry, went and cooled down, it solidified, and it formed a solid layer of rock. However, the magma itself will have solidified, in the case of a mafic magma, at a temperature of somewhere around 900 Celsius. So this rock is still extremely hot. It's still got a temperature of, let's say, 700, 800 Celsius. And so this means this rock is obviously going to steadily cool down, and as it cools down, it's naturally going to contract. And this contraction of the rock as it cools ends up forming these 5- and 6-sided columns, which we see as columnar joints. So this is the effect of cooling of a relatively shallow intrusion, which is pretty close to the Earth's surface. All right, thank you for watching, everybody, and have a good day.